Inside a conventional lithium-ion battery, movement is constant. As ions shuttle back and forth during a charge cycle, the internal components physically expand and contract. The liquid electrolyte accommodates this perfectly. It flows, shifts, and fills every microscopic gap as the battery breathes. Solid-state technology replaces that fluid with a dense, stable block of ceramic. But removing the liquid ignores a hidden physical reality. The internal electrodes still swell and shrink as ions move in and out. When a moving, expanding electrode is forced against an immovable ceramic barrier, it generates immense mechanical stress. The exact feature designed to make these cells safer, their absolute rigidity, is the same property that causes them to fail. To see how this happens, we have to look at the exact boundary line where the expanding electrode meets the solid ceramic electrolyte. In this cross-section, when the cell discharges, the electrode shrinks and pulls back. The inflexible ceramic cannot follow, leaving microscopic voids along the seam. This contact loss halts ions. They can't move through empty space, creating dead zones that kill power transfer. Engineers attempt to force these layers back together using stack pressure, an intense external force applied to crush the battery layers into constant contact. But ceramics are brittle. Constant volume changes and crushing pressure eventually cause the electrolyte to shatter, forming deep microcracks. Once the ceramic is fractured, the battery's structural integrity is gone, clearing a path for a much more aggressive failure. During charging, high current density causes lithium metal to deposit onto the anode, but it doesn't plate in a smooth layer. It forms jagged, uneven deposits. These deposits grow into thin, metallic filaments called lithium dendrites. They are opportunistic, exploiting manufacturing pores, weak ceramic grains, and mechanical microcracks. Driven by electrical current, these metallic vines force their way deeper through the electrolyte's compromised pathways. If a dendrite bridges the gap from the anode to the cathode, it creates a short circuit, leading to thermal runaway. While solid electrolytes were intended to block these filaments, rigid ceramics provide the exact crack pathways dendrites need to grow, a vulnerability liquid electrolytes don't share. Even if the structure stays intact, a quiet chemical conflict is happening. Many solid electrolytes, particularly sulfide-based ones, are highly reactive when touching lithium metal. This cross-section shows the interface where these materials meet. They react to form a resistive decomposition layer, a space charge layer, right along the seam. Every time the battery cycles, this layer thickens, catching and trapping ions as they attempt to pass through. This growth chokes off ion transport, essentially starving the battery of its ability to move energy. Even without a physical break or a short circuit, this chemical rot eventually suffocates the cell from the inside out. We are left with a cell riddled with dead zones, shattered ceramic, metallic veins, and chemical sludge. But these failures give researchers specific, measurable targets. We know exactly what must be overcome to make these cells viable. New designs are attempting to weave flexible polymers into the brittle ceramic to provide the elasticity the system needs to survive. Moving this technology from the lab to the road depends on creating materials that can withstand thousands of cycles of physical expansion and chemical reaction. Success relies on engineering a solid system that somehow mimics the resilience of a liquid, allowing a rigid structure to flex without breaking.